Thanks, Brian. So as Brian said, I'm Tom Phelan. I'm the chief architect and co-founder of BlueData, and I'm accompanied today for this session by Nanda Vijayadev, one of our data scientists. And I'll be talking about the lessons that we have learned in our journey of moving the Spark infrastructure into Docker containers. So let's begin. We got a lot to cover today. Outline is pretty basic. We're going to cover a justification of why we did this at all. So we know what Dockers are, we know what containers are, and we know what Sparks are, but why do we do this effort? Some challenges that we faced, lessons that we learned, and hopefully we'll have a little bit of time for Q&A at the end of the session. First of all, I'm talking about Spark within an enterprise. So data scientists are using Spark to mine data and provide value to the enterprise so to extend their business interests. Within the enterprise, we have this unique polarity between two different groups. One is the data scientist who wants to use the latest algorithms, the latest data, quickly and repeatedly extract their data and deliver it to their internal customers. On the other hand, we have the IT organization, which is tasked by the company of keeping control of security, multi-tenancy, resource usage, data access, and that sort of thing. So what we have is two competing interests. Data scientists want to be flexible, elastic, quick. IT organizations want to be careful, secure, and tend to be a little bit slow. The reason we approach Docker containers at all is to try to address the two concerns of these two conflicting groups within the enterprise. Before I go too much further here, I'll kind of want to level set what we mean when we say Docker, we say container, and we say Spark. Okay, there may be a little bit of review for the audience, but a container is a unit of virtualization that runs on a Linux platform. It is a methodology for encapsulating services to limit them to a certain amount of resources within the Linux box and access to certain either storage or network connectivity. A Docker container image, we'll use the names kind of interchangeably, refers to a file format that describes a stack of software that extends all the way from the operating system up through the highest levels of the application. When we say Docker container, it differentiates a little bit from your traditional virtual machine. The virtual machine typically describes only the operating system, and then the user must install their software on top of that. With a Docker container image, it installs not only the operating system, but the entire, whether it's Spark or whether you're using RStudio or maybe a notebook like Zeppelin or Jupyter, all those are specified in the Docker container file. And what makes it especially interesting is you can take that same Docker container file and run it not only on a public cloud, but also a private cloud. So what I have here on the left side and the right side, you'll notice are some values, those things which are important to the infrastructure team, the IT team, those values, things which are valued by the data scientist for the application. They're basically the same thing as, they're just different ways of saying the same thing, which are the value propositions of a Docker container. For the infrastructure, you have agility and elasticity. They lead to efficiency, cost reductions, also portability and standardization. When we say standardization, we mean not only around the software itself, but also the security models, network models, and storage models. So that makes the IT group happy. On the right-hand side, we have the application group, which is, in this case, the data scientist. What they want is foolproof packaging. So everyone here knows that there are sometimes issues with finding the correct versions of Spark and the Spark ancillary software so that they work together in a compatible way. They want to recreate and be able to quickly reproduce their environment. So if there's a mistake and they want to try something different, they can refresh the environment and begin again from a known starting point. And this whole faster and lightweight turnover allows them to do their job more quickly. So what we have here is good rationale for the IT staff and for the data scientists to want to move their applications into Docker containers rather than doing which is typical today, which is the installation of Spark on a collection of bare metal servers. Tends to be slow, tends to be static. With Docker containers, we can improve that agility. Okay. So now I want to say we've kind of had a justification of why we want to move the Docker or the Spark system into Docker containers. Next few slides are kind of a humorous look at some of the pitfalls that you might encounter as you go down this journey. And we have plenty of experience with this. So we talked to many customers who have do-it-yourself solutions where they've tried to use Chef and Puppet scripts to do some level of automation of bringing up of Docker containers and then installing and starting software. So it sounds very easy, right? You can start with a Docker image file and the Linux toolbox for containers, and you get your nice single container with some basic networking and basic storage. But this Docker containers toolkit is really built around the concept of a microservices architecture. What that means is that you have a single service running within each container. And as we know, Spark clusters are constructed of a sequence of cooperating services. So the first thing you need to do is how do you handle all those services? And this is where the pitfalls begin. Okay? You have a concept of container manager. Now there's a whole plethora out there to choose from. Kubernetes, there's special ones on AWS or Mesos. What this means is how do you allocate your container, how do you do some resource management, and where do you place your container across the various hosts within your, in this case, a data center. We'll talk about an on-premise data center. After you have selected some sort of container management system that's compatible with your enterprise, you have to worry about storage. Once again, do you use the overlay files? That's the typical way that you would use with a standard container application if you're a web-based application or so forth. Or you might want to choose something like Flocker or Convoy, which are the more container-specific methodologies for using storage with containers. Similarly, you have the same issue with networking. Networking, you have a close linkage with the selection for container manager. So you might choose Calico or Flannel or some other weave. But those, again, once you have to make sure you have the right plugins, and those right plugins work with the security constraints of your IT organization with your enterprise. So there's some thought which needs to go in place as you select what that network manager is. Always there's this line of performance. It's no good if the Docker container deploys your Spark cluster quickly, but it takes you 5 times as long to run the application within a Docker environment as it does on bare metal. It's just not going to work for the modern environment. Software configurations, we spoke about that a little bit earlier, but how do you make sure consistently that all your applications will actually work together and you can upgrade one and not the other and be sure that they're going to be continued to be compatible. And you'll make mistakes. We have seen this all the time. Enterprises put together an initial stab at rolling out an enterprise platform for big data, or in this particular case, Spark on Docker, and it works maybe for that first month in a POC, but then they forgot about scaling or they forgot about something else. But eventually they'll get to the top and they'll kind of get it working. And then that's when the real challenges come in, because that's when the security guys and the backup guys and the lawyers come into the enterprise and say, well, what about backup and recovery of data? What about true security? What about multi-hosting, multi-container upgrades and patches? These are all the things which really differentiate the kind of POC science project, do-it-yourself implementation of a infrastructure and something like BlueData, which is an enterprise quality solution. And at that time, we see people wave the white flag and either come to BlueData or to some other company that helps in how to Dockerize their Spark clusters. So that's kind of the difficulties involved. What I want to do now is go on to some tips and tricks of how you, if you are rolling out or if you're selecting a vendor to help you roll out a Docker container solution for your Spark cluster, this is what you want to look for. Okay. First of all, it wants to be flexible enough to run not only on-prem, but in the cloud. Even if your company today has a policy of only being on cloud or only being on-prem, we find that those kind of corporate decisions change rapidly. And so even though you may be all on cloud today, you may be on a hybrid solution tomorrow, and vice versa. Okay. And these are very complex distributed systems, so it can be daunting when you think of all the things which need to interact. Okay. What I want to say now is just some basic design decisions. These are not implementations, but these are things that we put in place when we first thought about, we laid down the architecture of what it meant for us to run Spark within a Docker container. One of the very, very first things we wanted to do, and this has dramatic impact on the entire design, is we wanted to run the Spark software and any applications associated with Spark entirely unmodified. We did not want to introduce any rewriting. We did not want to reduce any modification for framework scheduling, anything like that. We wanted to be able to take the software as soon as it came out of the open source Apache community, latest source, and within an hour or two have it running on the BlueData, in this case, our infrastructure within a Docker container. That was the #1 goal that we had. Number 2 is we wanted to make the deployment model to mirror as closely as possible a bare metal solution. So as you know, today you'll have a collection of physical servers. One of those physical servers will be the master or controller node for Spark, and there'll be one or more other physical servers which will be the worker nodes, and they'll be running different services. Similarly, if you're running R Hadoop or something like a Zeppelin server, those will be on different services on those same clusters, and so you have a different sequence of services. And we wanted to schedule them all the same. So as I said in the very beginning, the Docker container is typically designed for a microservices architecture where you're running one service within each container. But what we wanted to do is wanted to run those Docker containers but have them run a collection of services so they would look as close as possible as what they would have in a bare metal installation. That goes back to the first bullet item in our design decisions, which is to be as close as possible and not require rewriting of the application. Third thing we said is multi-tenancy is a key, and what we mean by multi-tenancy is security. So a tenant is a unit of security, network, storage, authorization, authentication, the whole 9 yards, built in from the bottom up so that it could be used reliably in an enterprise. Another design decision that we said is, this goes back to the first two, is we wanted only a single Docker image file. We felt that would be the simplest for the IT organizations and actually transfer of the information, rather than having multiple Docker image files. One image file that defined the services for the controller, another image file that defined the services for the worker nodes, and for other types of nodes. We didn't want to have to manage the movement and coordination of 3 different types or 4 different types of Docker image files. So what we wanted is this concept of auto-configuration. You had a single Docker image file, you used it to instantiate all your containers for your cluster, and then they would automatically differentiate themselves into master nodes or slave nodes or Zeppelin servers or whatever you needed for your application. That was key to our design, make it simple. The final thing we wanted to do is keep it stateless. Right? The whole power of containers is that they can be turned on quickly, torn down quickly, the resources used by another application. What we wanted to avoid is customers or users creating Spark clusters in Docker containers and then having them sit idle because they were fearful of tearing them down and the expense of having to do manual provisioning and put the live state back into those containers when they were reinstituted. So in order to keep that flexibility and agility value proposition of containers in general, we wanted to make them as stateless. And the few bullet items here indicate how we did that. Container storage is ephemeral, which means it's non-persistent in our organization. And all data, the big data that Spark is using, is stored outside the container. So it has state, but it's not part of the compute cluster itself. So getting into how we actually did this, talk about resource utilization. 2 primary resources are CPU and RAM. Since we're using containers, we use the standard C group infrastructure for quality of service management of both CPU and memory. One tip that we learned is we support over-provisioning of CPU resources, which means that the user can allocate more virtual resources than physical resources, and the whole idea there is to, with virtualization, do bin packing and run more applications on the same physical resources. That works well for CPU resources. We found that it does not work at all for memory. So we didn't even bother doing any sort of over-provisioning for memory. What we found is that once the host, the physical host itself, started to memory swap. The performance of the Spark clusters degraded so rapidly it wasn't worth trying to do that. So as you go forward, I would say let's limit your over-provisioning to CPU resources. Network, what we had to do is a couple of changes to what would be considered the default methodology of using containers with networking. So we assigned a fixed IP address to each container. What that allowed us to do is reboot the container or reboot the host and still have the cluster come back to life because the IP addresses did not change. We created, with part of our model for multi-tenancy, which is security, we created VLANs per tenant. What that allowed us to do is isolate the network packets between tenants. So even within a single organization, many of the customers that we worked with were governmental or legal or medical or financial, where only certain groups within the enterprise had access to certain types of data sets, and we needed to maintain that even within the network and the processing of the Spark cluster. And we did it with these VLANs, and we used a VX tunnel architecture to tunnel between the hosts. This is a graphic showing how that is, just in case if you're not familiar with how this stuff works. The two big gray boxes represent physical hosts. They have physical network interface cards on the bottom connected into a physical network. That's your standard network. On top of that, we create an overlay network. And what we have here is represented by the horizontal red line at the top of the graph, which shows the individual Docker containers being linked by private VLANs. And what I'm showing there is two different container clusters. It may not be as obvious as I would have liked, but we have a Spark cluster and a Hadoop cluster. Those are sharing the same physical network, but they're on two different virtual LANs. And so if you connect to one container, you can't do any packet snooping of the containers, of the packets belonging to another cluster because of the VLAN. Storage itself is always tricky. We tried a number of different techniques for attaching storage to the container. We tried overlay file systems first. We found out performance was not acceptable. We then tried attaching physical devices directly into the container. That was problematic because if you rebooted the physical host, the numbering of the PCI bus could eventually cause it to be such that when the system came back up, you reestablished or restarted the container files, but they were actually attached to the wrong disk. So we don't want to risk that sort of thing. So what we did is we laid down a Linux logical volume on all the existing either spinning media or SSDs on the physical host, used PV, which is the physical volume tool within Linux to partition up that logical volume, and then associated one of those PV devices to each of the containers, built an ext3 or ext4 file system on that, and that was the local storage for the container. We found that to be extremely performant and extremely simple to do. The last third bullet item here on this first storage component is a reference to some BlueData technology, which provides a fast mechanism for accessing remote storage. That's not the purpose of this talk, but that's to get back to that initial design goal, which I mentioned earlier, where the container only had ephemeral local storage or non-persistent local storage, and all real, true big data was stored remotely from the cluster itself. Image management, we just use a standard registry, Docker image files when we built up a library. BlueData provides a number of predefined images, but all our customers make their own. We'll go through how that process works. Security, as we said, is built in from the ground up. This includes not only network and storage, but also the container itself. Now, over the last 18 months, the security of the Linux container infrastructure itself has greatly improved, but you still see typically when you're looking at people using containers, they say, oh, just run it as root. That'll solve everything. Just run it as root. It'll have all the permissions on the host. That completely does not fly in the enterprise. You have to run them as non-privileged users to limit the attack plane from the container into the host. So that's what we do. We run them as non-privileged containers, and then we carefully use the capabilities associated with the container and give them the absolute minimum amount of capability required or needed for them to actually do their job. This is a list of the typical capabilities that we enable for a container. It would be a starting point for you to work from as you go through this process. This is a sample Dockerfile. If you're familiar with Dockerfiles, this is just what you normally see. I'll quickly go through what this actually means. On the very top, you see that we're starting with a CentOS 6 image. So we have the operating system image there. We then want to load, in this case, a version of Spark 201. In addition to the Spark, we want to have in this cluster a Zeppelin notebook. So we'll add that software. And then these last two lines are the BlueData IP, where we selectively auto-configure the containers based on information which is provided to the cluster at runtime. This allows us to use a single Spark image, a single Docker image, and then differentiate it into different services. And so I wanted to show that on the next slide. But this slide here is just another description of an image. In this case, we just call it an app image to differentiate it slightly from the standard default Docker image file. So a BlueData or app image is consisting of a doc image on the left-hand side. Those are the software bits. On the right-hand side are some particular information about the configuration. Those are joined in the runtime, which are a series of init scripts. So by default, if you use a Docker container or a Linux container in general, it does not have the concept of startup scripts or init scripts. We built that in so that the container behaves more like a virtual machine than just a simple container. All those built together become the .bin file, or in our case, the specialized Docker image file. To get back to the previous slide, I wanted to show very simply what it actually means to run different services. What we have here is 2 physical hosts. I've logged into 2 physical hosts, and we've started 4 containers. Those containers each have an individual persistent IP and are attached in a VLAN, so they are a cluster. Logging into 2 of those, or SSHing into 2 of those containers, I just did a simple PS and to see, okay, I started with the same or a single Docker image file, but now I see that I'm running different sets of services depending on the type of use of that container, whether in this case it's a controller or a master or a worker. This is a snapshot of the mapping of what we did for storage. Now I explained that we used logical volumes on the base and then physical volumes for the storage for each of the containers. This shows the mapping between the 2. Everybody about this time asks me about performance. Well, Tom, this is great. I like the simplicity, I like the flexibility, but truly tell me about the performance. And we did a lot of work on this. So what we did is we tried as best we could to put together an apples to apples comparison. In the information I'm going to show here, we happen to run this on a 10 physical host cluster. We've run this up to 100 physical hosts, so the scalability, horizontal scalability is present. What we did is we selected a standard micro benchmark, in this case Terrasort, and a version of Spark Yarn. We installed it on bare metal just as it would normally be done by the supermajority of users of Spark today, ran the Terrasort. Then what we did is use those exact same servers, restore the software, put our BlueData container managed system on that, reloaded the same distribution of Spark and ran the same tests. And what we found is the performance is approximately the same. So all the way up from 100 gigabyte to, in this case, a 1 terabyte data set. There was no appreciable differences between 1% and 3%, one way or the other, of the performance of the bare metal. So there was no impact on performance of running Spark within a Dockerized environment. This is a couple of shots just to kind of understand the power of what you're getting. One of our goals was to make the experience for the data scientist as close as possible to what they experienced during a bare metal installation. What I'm showing here is just a rendering of a 6-node Spark cluster, and we have specified the URLs. In this case, you have the Spark worker and master URLs, and also a notebook URL. If you click on that notebook URL, you'll come up with the exact same web-based experience of that notebook that you would experience in a bare metal environment. So we have customers that use this tool and they never tell the data scientists that in fact they're running on a virtualized or a Docker environment. It behaves just as if they provided them the IP address for a physically configured cluster of Spark. This is a snapshot of some images that are currently available. All I want to show here is that pretty much any big data application can be Dockerized. I know we're talking about here, since we're at Spark Summit, we're talking about Spark and we're focusing on that. But we can also do Cassandra, Hortonworks, Hadoop, RStudio, Kafka, what have you. They all can be packaged into the same architecture. The reason this is possible is because we've said, I remember our goal was to run any application or big data application completely unmodified. So it's very easy to port these. All it requires basically is editing the Docker image file. So no additional software work required. Just a little bit about the on-demand and elasticity. So if the customer or the data scientist knows that they're going to be running a very large job, they'll want to provide or want to request different amounts of CPU and RAM when they construct their Docker containers. This is how they do it. They select either through a RESTful API or a UI. Said, hey, here's my Docker container, but make sure that I get this amount of RAM and this amount of CPU processing because I'm going to put a real big job on this cluster. And what I want to show by that bottom TTY, the login, is that you can go ahead and install any software you want. Since these containers are essentially managed and configured as virtual machines, they're identical in most respects to that for most users. Okay, some key takeaways. We've gone through a lot of information, you know, what Docker containers are, Spark, how we did it. Now just to kind of think about the value add of what this gives not only to the IT department, but also to the data scientists. So I'll be providing key takeaways from both perspectives. In this case, this is kind of an IT perspective. Any application can be Dockerized, including Spark. It gives you that flexibility and agility, the DevOps solution. However, that last item, we're providing DevOps not only for your developers, but also for your data scientists, this quick turnover, repeatability, okay? Deployment requirements, this is absolutely an IT request. All images, all software is bundled together into single image files. Orchestration is tied in with the enterprise, along with networking and storage, and monitoring for both CPU and memory. Can also do billing based upon those. In terms of the data scientists, this is all the things that they want. It gives them the flexibility, the repeatability, deployability, all the things which allow them to get to DevOps and really streamline their usage model of the system. Some of the challenges that we face, and we have already covered these, we get automatic integration of LDAP and Active Directory. That was one of the big things. As soon as we went to the enterprise, they said, this is great, but and you've given us network isolation, you've given us storage isolation, but we need integration with our enterprise authorization and authentication. So we implemented the LDAP Active Directory integration automatically. And this runtime injection of resource and configuration information allows us to do the auto differentiation of the container image as it starts. And finally, this is kind of a word of caution if you're doing this yourself. It is time consuming, it can be costly, but there are people out there who have done it. I hope I provided you a little bit of information that you can take away today to do that. Or you can come to us or AWS or another kind of a Docker Spark as a service solution. I'll wrap it up here and take any questions. If there's more information, please come to our booth at K8. Sure.
Do you have any suggestions or recommendations for streaming? Implementing Spark streaming on Docker?
Nana, do you want to talk about what we've done for streaming here? We've actually taken a number of applications, streaming applications, and done that, but I'll let Nanda fill you in on it. I think you can ask Brian for the microphone.
Yeah, I think like Tom mentioned, for us, we concentrate on running applications unmodified. So some of our users who use streaming, they either go with Kafka streams or go with Spark streaming. That application runs based on how they've built their existing pipelines. If you're talking about streaming in terms of latency or the batch size, specific things like that, that's a configuration that they control. Is there a specific aspect of streaming that you're further interested in? Yeah, streaming is yet another application that runs on BlueData, and choice of what type of streaming users use is dependent on what they have identified as their type that they would support. Like I said, it could be Kafka streams, or it could be Spark streaming, and there are people who have built their own streaming technologies that they'd use. Any application runs in our platform that is certified by the enterprise.